Yeah. Hello.
Okay.
How are
Hello.
you? Yeah.
Good
Yeah.
to see you. Okay. So
So
everyone,
other one is
yes,
going on.
yes, everything is good.
Oh,
Okay.
okay.
So I now we will go to the last presentation that will be presented by Ranajit Sai from Tyndall National Institute in Ireland.
Mm-hmm.
Title of the talk is the High Frequency Integrated Magnetics for High Performance Computing. So I will
Correct.
stop the sharing and you can start your presentation. And just for your
Okay.
information, the meeting is recorded.
Okay. All right. No problem.
Okay.
Give me a second. Uh, okay. So can you see my screen?
Yes, we can.
We can see, but now we see the Teams applications.
Yes.
Okay, now it's the presentation.
Let me go to full
Okay,
screen.
good.
Is it fine?
Yes, please go on.
Oh, I can start now. 2 minutes early. Okay. Okay. So thank you very much for calling me in this, and thanks to Veda and the InfraChip team as well. And it is my great pleasure to represent Tyndall's power magnetics activities in front of you. Um, it would have been nice if I am there. So but it's a new reality now, post COVID, that we are having so many online meetings. Okay, so welcome to my talk. Please let me know if you are having any difficulty in hearing me or seeing my screen. And in fact, if you have any question or something, I would prefer that if you can stop me, and we can solve those problems right away there itself as well. So this is how we should go ahead. Okay. So I'm Ranajit Sai, Integrated Magnetics team lead and senior researcher here. A bit of background about me is that I did my PhD from India, and that is in 2023. It's not 2023, 13. And then I spent 4 years in Japan, and then another 4 years in India as a faculty, and then joined here in Tyndall in 2022 May. Okay, so today I will be presenting high frequency integrated magnetics for high performance computing. So a very specific application area where we are mostly focusing on at this moment, and the kind of high frequency integrated magnetics technology we are developing, a bit of work what is going on around, and bit of work what we are doing, I will be trying to showcase in front of you. This is our team. Professor Kiano Mahuna, he started these activity, integrated magnetics activity, I think 30 years ago or so. And then Mr. Mike Hayes is also here. He is the head of the group for ICT for energy efficiency. I'm there, and we have a program manager to handle various industry funded project that we get, so that we are not meandering around, and we are delivering on time on whatever is needed. And here are our researchers group. We have mostly postdocs, 5 of them, and one PhD student. Apart from integrated magnetics team, we collaborate with our internal members from MCCI, which is a microelectronic circuit center, and Dr. Sema Sodriskal and Dr. Hugo Cruz, and Dr. Shambuddha Khan is from PHMMs, and he is a fabrication expert. He gives us a lot of help in kind of fabricating our inductor devices. And I would like to say that we are expanding, and if any of you are interested, reach out to me. This is the 4 pillars of integrated magnetics research in Tyndall. It starts from the materials to device, sorry, and the materials to device to circuits and systems, and even the PMIC, the power management IC. So the MCCI colleagues, they design the power management, and our other MCCI colleagues, they design the circuit, and we design material and devices appropriate for those circuit, appropriate for those PMIC, so that we have a full voltage regulator ready with us in some way, and we do the packaging in-house in Tyndall as well. This is about our activity. You can see that various kind of magnetic materials we develop in-house, and kind of magnetic composite which has magnetic particulates material along with some epoxy or some polymer binders. And then we have anisotropic thin film, isotropic thin film, and a variety of inductor construction structure like vertical inductor, solenoid, stripline, toroidal, and so on. So I'll be touching a few of them in today's talk. This is in a nutshell what is our integrated magnetics group looks like. As Kian usually say that it is overnight success after 30 years. So it's actually a lot of effort over the past 2 or almost 3 decades that has been gone into it. And we have achieved quite a few interesting devices, and we have some a joint patent with Apple, as well as top 3 global semiconductor companies. We have multi-million dollar, multi-million euro licenses. And among the key facilities, you can see that typical measurement capabilities we all have, electrical testing we have. But interesting thing is that we now can characterize those inductor devices at higher current, at higher frequency. Typical measurement is done in VNA or impedance analyzer, which can handle only a few milliamps of current. And so the measurement data is not the true reflection of its in-application behavior of the device or of the material. So we have developed a technique right now, and we are actually still working on it. So at this moment, I can go comfortably around 30. And if you wish 50, maybe you have to wait for another 2 to 3 months or so. We'll see. And there will be some publication coming out later this year on this. And here are our industry partners. Some of our present partners, some are old partners. You can see all the big names and usual suspects in this integrated magnetics area that we have worked with. Here will be sorry for my throat. So I had a travel to APEC, Applied Power Electronics Conference in Atlanta, returned back last week, and since then my throat is upset. So bear with me, please. So we will go through a brief introduction of integrated magnetics for powering microprocessor. What's the need, why, and how we can integrate the magnetics, and then some of the magnetics research that we are doing, some innovative structures, and some new efficient CO Epi-based material, alternative to the popular CGT-based material. And I will touch upon a little bit of on the heterogeneous integration of magnetics on silicon by microtransfer printing aspect before concluding the talk. So we are talking about the powering microprocessors, and the system level efficiency is very important. So what happens is that we take the power from the mains, and then it is going to the motherboard, and it is going through various stages of power converter. And if you know that there are two classes of thinking, one is that you have the final stage of voltage converters outside the chip. This is your chip, and then from outside chip you supply individual core or different IO and other aspect of other parts of the processor. In the second way, you have a robust high efficient stage converter, and the last stage to be placed inside the chip. The question is which one is beneficial and which one is complicated. So to answer that, there is a fantastic paper which has studied this issue, and it was found that if I quickly take you through that what is there in this particular slide, here you are seeing that this particular example has 4-core processor, number 1, 2, 3, 4-core processor, and 3 different workload are distributed in those 4 cores. So for example, the workload 2, all core are equally utilized. But for workload 1, your core 1 is mostly used, core 2 is least used. But if you are supplying power from outside to all core, then you have to give an overhead and a huge amount of power you have to provide. And that creates a lot of additional power which is not needed, but you have to deliver to the processor. And that means that will eventually end up in the form of heat, and you are losing a huge amount of efficiency, system level efficiency out there. How about having a per core regulation? If we can deliver the low power to individual core of the processor, then it can be much efficient. And this paper is talking about some 20 to 25%, 30% efficiency can be increased. And some other reports are there under different circumstances when there are more number of cores, it can reach even more than 50% efficiency increase. So you can simply double the battery time in some way if we can enable per core regulation. So important thing is to take from here is that granular power for microprocessor, sorry, it's efficient, it saves energy, and this is the way forward. The question is, how is it possible to cramp so many power converters, the whole power converter, which if it's simple buck converter, then it will be like one PMIC, two capacitors, one inductor. So the all three things, all four pieces of devices has to be together inside the core or very close to the core in some way that you are reaching each core separately. And for that, you need frequency innovation. There is no other alternative. You have to go to higher frequency, and higher frequency will reduce the required inductance value, and the small inductance value then can be integrated, on the silicon or in the package in some manner, and then you can hide it inside. So that's the way, and that's how enabling kind of magnetics disappear into IC. We know that in terms of the cost, size, and weight, moving from traditional low frequency device to system to high frequency system has all the benefits. It's all looks good, green. The switching frequency going up, energy storage requirement of power converter will come down, size of the passive component will come down, loss of turns, a number of turns will come down, cost will come down, and so much benefit. But with switching frequency going up, magnetic core loss goes up. Question is that will it be still beneficial to have higher frequency application? And there we have to assess whether the loss at higher frequency is really prohibitively high. That's the question. Now, in this plot, it's showing that variety of magnetic losses that happens in a power converter core. There are typically three big classes of losses. One is hysteresis loss, one is eddy current loss, another is anomalous loss. Here we have plotted the energy loss per cycle, so divided by frequency, please remember it, and versus frequency. So we can see that the hysteresis loss at lower frequency is the dominating loss. So we have to have a super soft magnetic material. But if you go to higher frequency, hysteresis loss is not a big concern. The biggest concern is the eddy current loss and anomalous loss. And that means we need to have a magnetic material which has much lower eddy current loss and much lower domain wall motion related loss, which is essentially kind of excess eddy current loss, you could call it. So it's a different, it's a paradigm shift in some way in choosing appropriate magnetic material for this high frequency application. And to do so, we have to see that eventually the fabricated inductor, where will it be located in the package? If we identify a magnetic material which will require a very high temperature processing, despite its goodness in terms of its performance, it will not be useful because it has to be integrated in the package. So we cannot fabricate a very high temperature material through this for this particular type of application, the power converter application for microprocessors. So typically two classes of packaging solutions are possible. One is on silicon or in the interposer. Something like the magnetics can be on the final load silicon, or it could be in a PMIC chip itself that is also on silicon, or magnetics could be inside in the package substrate inside the PCBs, either with a magnetic material involved in it, or a discrete component piece itself is buried inside the PCB chip in that way. So there are these two classes of magnetic material or inductor device integration strategy. One is on silicon, another is in package. And in Tyndall, we do both. Before that, I would like to show you a couple of examples how industry accommodated or evolved over the years in this particular area. This particular example I'm showing here is from 2018. This is Apple A12 chip, and it has this PMIC here and this Apple A12 processor chip over here. This is from iPhone XS Max model. What you are seeing here is that this PMIC is surrounded by 24 inductor pieces. Okay, and not 24, 12 inductor pieces. And that indicates that there are at least 12 buck converters or something like that. And each converter is powering these processors in some way. So if you consider the length from this particular converter to somewhere here in the processor, it is about 2 to 3 centimeter long, and that has to go down to the PCB board and then going along the PCB board and then going up to the processor load. So that's a long route that the current has to cover, and that will have a lot of losses. But that was the state of the art in 2018. What has happened in 2021 in Mac M1 Pro or M1 Max processor is something extraordinary. Let me explain it to you. What you are seeing here is this is the processor, and here the white color thing is the heatsink, and you can fold it over here something like this. So this block will go behind this one, and if you see, there are 1, 2, 3, 4, 5 power management ICs, PMIC are there. But curiously, here around the PMIC, there were inductors. And here around the PMIC, there are no inductors, all are capacitors. The question is, where have all the inductors gone? And this was really surprising in some way. Now, if you cut it down along this, including the processor, and there are these tear down images available online, then you can find that this is the top heatsink, this heatsink. Below that, this gray color thing is the processor. Below that, this is the interposer, and in the interposer here there are some silicon cap capacitors. Below that, this is the package substrate. And the other side of the package substrate, there is another one silicon piece that is one of the PMIC, one of the 5 PMICs. Still, we couldn't find the inductors. And if you look closely here, in this PMIC chip, the top view of PMIC looks like that, and it has 28 inductors, and each of them are coupled inductors. And if you cut it top to bottom in one corner, then you will see this image, which has the PMIC here underneath here in some layers. Then above that PMIC, there are these bottom magnetic layer, then 2 copper and top magnetic layer, which is a classic coupled inductor structure. And the top and bottom magnetic layers are cobalt, zirconia, tantalum based magnetic material. And this is something marvelous, because what you could see is that there are very tiny 28 coupled inductors within one PMIC, and in that way there are 5 PMIC, total 140 power converter phases. So in this particular model, they can give power core regulation. and that has its own benefit. The battery power, and through other engineering, of course, the battery power has gone up significantly. When the previous generation of Apple computers was lasting around 9 to 10 hours in one charge, and the current generation is lasting around some 18 to 19 hours, in close to 20 plus hours in one charge. So kind of double the battery power. That was significant. So that's where the integrated magnetics is very interesting. Now, another story is the Intel story. If some of you recall or know about Intel's journey on the magnetic inductor development, the on silicon magnetic inductor, like those coupled inductor you have seen in the previous slide, Intel was developing those kind of thing in 2009, 10, 11, 12. At that time, when I was student, I used to read those papers. Now, all of a sudden in 2016, 17 onward, they have moved their direction to a package-based solution. What they have done is they have used the thickness of the package to, and there are these plated through hole via structure. I mean, if I go back, you could see this package structure has this different via from top to bottom plated through hole. So something like this. And they use this plated through hole surrounded by a magnetic material as an inductor. So they are hiding their inductor inside the package substrate. So when the signal is going from below to above, PMIC to the load, on the way inductor is fabricated. That was a very clever solution, and it has shown a huge benefit. Something like the current density has gone up by 5 times, and inductance density gone up almost 10 times. That was amazing. However, here the permeability of the material is just 8. It is being operated around, say, 80 megahertz, 90 megahertz in this kind of high frequency number, but the 8 is good enough at that frequency number. So that's how it has evolved along the two of the big industry, and there are so many other industry that have looked into this particular technology. Now, in Tyndall, we do both kind of thing, in package as well as on silicon. And I will, some of the green color things are our ongoing research activities. We are working on the substrate embedded magnetic composite and cobalt-based thin film alloy, Fe-based thin film alloy, and cobalt-based vertical inductor structure, and some new development we have initiated, something like on silicon ferrite or thin granular films or isotropic granular films on silicon. I will take you first the in-package activity of what we are doing. So here, this is how it is in terms of the concept. You start with a polymer composite matrix or a surface passivated soft magnetic material, and then make a magnetic block, or here in this case a slurry, and then fill this, and then you will get a filled composite core, or position the core in the cavities by pick and place method. And after that, you have to do a via drilling in this, and then plate it through copper, and then you connect it where it is needed, and your device is ready. It is just like the way Intel has done. So that's the process. But the key thing is here, how you are making this magnetic material. That permeability of 8 can come down to 1 or 2 very easily if your engineering of this material is not good enough. And if you get high permeability, loss can go also very high as well, because the objective is to have low eddy current loss so that two particles are not touching. If they are too far away, loss will be low, permeability will also be low. But if they are touching, then permeability will be high, loss will also be high. So we have to make a balance, and that's where the surface engineering comes into picture, and a lot of research is required in this particular area, how to make this composite core appropriately. And here there is a typical structural flow of the project. If we wish to improve the material, something like we start from the alloy design, the what kind of alloy to be used, and using different modeling software, understand the what sizes of alloys is needed, then fabricate those alloys and do the first surface functionalization. After that, you fix how to make the core, and for that core making, you need to apply some software tools to identify what kind of size combinations will be suitable to give you the maximized maximum utilization of the space or the volume. And in doing so, I'm giving an example here. We did some alloy design, some very fancy EPI-based material. Then we get them fabricated through our partners and collaborators. And then we did some ball mill to thin it down to appropriate size and appropriate thickness. And then we make a heterogeneous particles. Sometimes we use spherical particle only, but with different size distribution through some simulations. And then we do some sort of a surface treatment. And once we do the surface treatment, then we have a nice coated particles or flakes. Then after getting those things, we make kind of some test core. And you see that during the making of test core, we have to be very careful about the pressure we are using, because the porosity matters, and porosity will change your material's property and the core's behavior eventually. So there are so many different parameters to play with, like different fillers, polymer brush behavior, different binder, and different solvent, and etc. So it's like a multi-parameter optimization process. And through this optimization process, you will get different kind of inductors. This is too busy slide. I'm not going there. Just I wanted to show, in some case, if you get high permeability, these blue color towers, then you are getting low Q factor. But if you are getting high Q factor, your permeability is low. So this is the kind of trade-off one has to play with, and then optimize the process. Then after some optimization, here you can see this the quality factor of the core material. If it is high, permeability is low, and if the permeability is high, core is low. Ideal target is to go somewhere around 80 permeability, 80 core Q factor, but we have got somewhere around 40. So we can call it that we are halfway down, and there is still enough room to grow in some way. Okay, so moving a bit forward, I will give you some example of on silicon magnetics activity that we are doing in Tyndall. And this is one example. It was in 2020. We have worked with Global Foundry closely and to fabricate some solenoid inductor structure on silicon. What you are seeing here is this a solenoid structure, and below inside this solenoid structure there is a magnetic layer. Here is this cross section. This is the solenoid top copper, and these are the bottom copper, and in between top and bottom, with some passivation separation, you have a magnetic thin layer which is about 5 microns, or rather 4 micron thick, and this thickness is actually comprised of very thin lamination structures. Sorry. So those laminations are cobalt, zirconia, tantalum, boron based magnetic film layer, 16 of them. Each of them are about say 250 nanometer thick, and in between two magnetic layer there is a separation of aluminum nitride, which is about 20 nanometer thick. Okay, so that's the structure. Once you get the structure, you'll see the very high quality materials property out of the structure, and that is reflected on the performance of the inductors that has been fabricated over here. You could see this the very high inductance value, even up to 100 or even 200 nanohenry can be achieved, which are working about some 40-50 megahertz. If you see the Q factor of this, the red one, which has 100 permeability, has Q factor of 20. This is device Q, this is not the material Q only. So this incorporates the copper turn and the losses related to the copper turn as well. So the material quality factor is much higher than the 20. So overall, this is a fantastic demonstration of a very high frequency inductor. If we choose the design appropriately, such as in case of this SL1, we can extend the operating frequency to almost close to some 100 or 200 megahertz, and the peak of quality factor is coming around say 100 plus megahertz. So this particular material can be useful for 100 megahertz application as well, easily. Now, this was the old work with cobalt zirconia tantalum based material. The question is that what's next for magnetic material development on silicon devices? So there are two approaches you can improve the devices. One is that you change the inductor construction and come up with some fancy idea. And thin film vertical copper pillars is one of them. I will talk about that. And then we have done some improvisation of the choice of material. If we choose a high performance material, better performing material than the state of the art, like the cobalt zirconia tantalum or cobalt zirconia tantalum boron based CGT or CGTB based material, say Fe based magnetic material can have 1.5 times more BSAT, that means better current handling capability, and 2 times higher resistivity. It can be even higher, but 2 times we are demonstrating here today. 2 times higher resistivity means uh, the eddy current loss will be significantly lower, maybe 4 times lower at higher frequency than CGT. So that will give the efficiency a real boost. So the why and how the vertical structure came is that the Intel used a vertical copper pillar, or rather plated through here, but structurally looks like a copper pillar, hollow pillar, and surrounded by a magnetic material. Apple has done a horizontal copper bar surrounded by a magnetic material around that. So it is like a pillar falling down and staying on top of a silicon substrate. Interesting thing is that this pillar has a magnet, this coating on this horizontal pillar has a magnetic permeability of 300 plus, whereas this pillar magnetic permeability is just 8. The question is, can we make a vertical pillar with a thin film around it? Then we can get, in a very small pillar, we can get significant amount of permeability out of that, because the permeability is almost some 20 times more. That brought to this vertical inductor concept, and it is now patented by Tyndall. And what you are seeing is that very it's just 100 micron tall pillar, and those copper are connected underneath. So this is basically one turn, not one turn, one inductor connected to another inductor in series, and then they are 2 terminals. Now, if you deposit magnetic material around it, the magnetic material will look like this. At the bottom, it looks like that. On the side wall, it looks like that. You see that those laminated structures are still there. So after polishing this top mushroom-like structure, you will get nice copper pillars. And these pillars array can be utilized to connect appropriately wherever is needed to route the current and get the necessary inductance. A quick comparison through some simulation we have tried, and just I wanted to see show you this particular one parameter, L by RDC. This is kind of a quality factor that the per unit milliohm, how much inductance you can get. You could see that Intel's composite core, with respect to that, it is 25 times more. Now, if you make those copper pillars wider, that we can make with fabrication process, then it will be even more, and that is amazing to see. We are working on it. There are some technical challenges to get to the final working device, but we are on the way. The last bit is here is that I have another 15 minutes, I believe. Okay, so last bit here is this the iron based anisotropic film. how we can get about that. So we have deposited some iron, cobalt, nitrogen based magnetic material, and after thorough material research, material search and development and process tuning and etc., what you have found here is that the resistivity of the film can go up to 200, whereas the standard CGT is 100. So it's 2x more resistive, and its stress is also quite low. And that means it will not be prone to delamination or structural issues, and that's great. And it has a BSAT value which is very close to 2 Tesla, and that was amazing. So in that sense, this material, that FeCO B-based material, can be very useful. And we have tried various sister composition of that, and we have found that the FeCO Bn based material is one of the best candidate to explore for future generation of magnetic materials for thin film application. The last section of my talk is on the heterogeneous integration of magnetics on silicon. So what you have seen is that we can get a full wafer full of magnetic devices. Okay, and now idea is how we can use those magnetic devices along with other sources to put them together to form a circuit. Here, something like that, what you are seeing is that there are two test inductors. They were placed side by side along with three capacitors just to make a simple filter. Here we have used copper, sorry, the gold wire bonding, but we will be in actual application, we will be doing lithography on top of that. And so here, but these two devices and these three devices were not handpicked and placed. They were used by a machine micro transfer printing, a automated process. The micro transfer printing is a very popular process. So we have inductors, and these inductors are of this size, and so we have micro transfer printing. Sorry, sorry, yeah. So we have this micro transfer printed devices here, and you could see that these sizes are not too small, though it looks small with respect to the hand, but they are not very small for micro transfer printing. Micro transfer print as a technology is developed for photonic devices, and they are much smaller. So the standard micro transfer printing process won't work for our process, for our devices. We had to kind of come up with a non-tethered, a new process where we are kind of backgrinding the substrate after micro fabrication of inductor with a glass carrier, and then backgrind it down to 250 micron. We can backgrind it to 50 micron, but here we have used 250 because the other capacitors were 250 micron thick. So to match the thickness, then we use a PDMS stamp to pick it and place it some foreign substrate, something like one wafer you have, and you pick from another wafer and place it over here. If I go back to one a couple of slides here, so what you are seeing is that imagine you have a PMIC wafer. This is source one. You have a capacitor wafer from somewhere, or chip capacitor kind of tray, and you have an inductor tray or inductor wafer. Idea is that they have to be sitting side by side and then connected to form a converter, just exactly the way that LED displays are prepared with three different color LEDs placing side by side for one particular pixel. So the similar idea is employed here. Then using microtransfer printing, you can block transfer from one wafer to a target wafer and place them appropriate locations with a micrometer level accuracy. And if you can do that, the whole new wafer with full of converter can be fabricated easily, and then you dice it and you will have a chip converter ready in front of you. So that's the idea. We are going behind that. We are on the way here again. So we have shown some um, uh, filter as a demonstrator, but we are trying to work with the PMIC team and the circuit team to come up with an converter demonstrator. And here I will end the talk with this particular video. So this is a video. Let me see how I can show it. Okay, so this video is showing that I will play it, but before that you can see that this is our source target, source wafer, a piece of wafer, a coupon, which has the diced inductors, but they are side by side there. And we have on the other side another wafer, which is the target wafer. This machine will pick from here and place it there, and then go for cleaning and come back. So let's see. So what you are seeing that it came, picked and placed somewhere. You could see that one die is picked from here in this zone and placed over here, yeah. Then it is coming back, it will peak again. So it was it was trained to do so. I mean, it was coded appropriately with LabVIEW code to do so. You pick the second one. Now it will pick the third one. Interesting point to note is that they are picking from one series but not placing it in a series. They can place it wherever you want in XYZ. You see that they are placed in 3 different locations. So this is how it works. And if you have multiple PDMS stamp, you can pick multiple and place multiple appropriately. So it is a highly scalable process and a fantastic approach to do a highly tightly integrated power converter design. Now, we knew that we have a magnetic material which are very delicate to different processes and so on. Its magnetic property get upset, and as a result, the magnetic property, if the magnetic property is not hold, then your inductor property will not be intact. We have done a thorough statistical analysis at different stages, and I have seen that our most of the variation are within some 5% or so, whereas if you go to any data set, you will see inductor with specification which is altering around plus minus 10%. So we are much better than off the shelf inductor in that sense. Okay, so that's where we are at. So here is the concluding note. We have developed some magnetic composite, interesting property with a very high Q and moderate permeability, and we have another material which is about 34, 35 permeability and around 40 Q factor at 10 megahertz, and this is at 25 megahertz. On silicon magnetics, we have shown you that how copper pillar can be utilized to come up with a new idea of a vertical inductor, and a new high BSAT FeCO based magnetic material with a very high resistivity is developed and can be used for future generation of power converters. And lastly, I have shown you or demonstrated you how heterogeneous integration of on silicon magnetics is possible through microtransfer printing to enable tightly integrated uh, converter design. Thank you for your kind attention. I would be glad to have any questions or comments on this presentation. Thank you very much.
Thank you, Ranajit, for your very nice presentation.
Thank you.
I will check if we have any
Yep.
questions from the audience. I don't see. Let's wait for a few seconds, maybe.
Yep.
Meanwhile, I just wanted to ask you from your presentation, and I understood that in Tintal you can do full material engineering of these magnetics, yes?
Correct. Correct.
Okay, and also processing and this transfer printing.
Yes.
Okay,
And the full suite of characterization of these magnetic devices, both magnetic material as well as magnetic devices.
okay,
So if you have thin film or powder magnetic material, we can characterize the magnetic material, its say coercivity, saturation magnetization, permeability, hysteresis, the anisotropy behavior. We can do a full wafer characterization as well as small sample characterization.
okay,
And on the device, all sorts of VNA impedance analyzer measurement, LCR meter, along with very high current setup that we have now, and we are now developing, and can go up to 30 megahertz at this moment today, and but will be ready for up to 50 megahertz measurement maybe in 2 3 months time. So that is also possible, we can do it.
okay. Thank you.
Mhm.
Okay,
So
I don't
if
see any questions from the audience.
Okay, fine. So I think you have my email ID. If there is some questions or some comment came in, please feel free to write to me. And I have not written my email ID here, but my email ID is my name dot surname at tyndall dot ie. Okay, so
Okay,
I welcome any comment or questions. If you have, feel free to write an email to me. Thank you.
okay. Thank you again for your excellent talk. Okay,
Okay,
so this was the
thank you then.
uh,
Yeah,
the
yeah.
last presentation of today's digital webinar within the InfraChip project. So once again, thank you to all the speakers and attendees for being with us. And I encourage everyone to visit the InfraChip website to see our offer on trainings and research infrastructures and apply for access. So I believe that this InfraChip project is an excellent opportunity to get free
Yes.
of charge access to the state-of-the-art infrastructure and boost your research. So thank you again. We are now closing the meeting and stopping the recording.
Mm.
Thanks again.
Thank you, everyone. Bye bye.
Bye.